This video covers the last 2 pages of that very long torque worksheet. We have 2 wheels, one with a large diameter, a diameter of 50 centimeters. Let me just show you that. It has a diameter of 50 centimeters. The other one has a diameter of 30 centimeters. You have 2 torques on here. One is at an angle of 90 degrees. This torque over here. So we don't use any trig on this one. This one is actually not 30 degrees, but pay attention to this one. This torque angle actually is 120 degrees because 90 plus 30 is 120. So what's the question here? What's the net torque? Let's identify the positive and negative torques. This one is going to make the wheel go counterclockwise. So that's the positive torque. And this torque will make the wheel go clockwise. So let's always start with the counterclockwise torque, which is the bottom left. So sum of the torques. This force, well, they tell you that both forces are 50 newtons right up here. Yep, both forces. Let's label this. Let's put a if there's not a decimal point after all your numbers, put them now. So 50 newtons, and this is also 50 newtons. This one at an angle of 120. So the counterclockwise is 50 newtons times the moment arm. And let's take a look at the picture. It's 30 centimeters, so 0.30 meters. That's the positive torque. And the negative torque is the torque that is 50 newtons sine of 120 degrees. That's the force. Times the moment arm. Look at the picture. 0.50 meters, 50 centimeters. So what's 50 times 0.3? I can do that in my head. 50 meter newtons. I think that's right. Yeah. Minus, and I've got to get out the calculator. I think this is actually, yeah, this looks good. Let's do, I go backwards. I just do it like this. I do 120, sine button, times 50, times 0.5, mess that up. I think I'm in, well, I know what happened. I think I'm in the wrong mode. I think I'm not in degree mode. No, I'm good. Okay. All right, so let's try it again. 120 sine times 50 times 0.5, so you get 21 point, this is wrong, what's going on here? Oh, that's right, okay, so it's minus 21.65 meter newtons. So when you do 15 divided minus 21.65, you get a negative 6.7 meter newtons. So the torque is a negative. So the counterclockwise torque is the big one, I guess. Yep. No, the clockwise torque is the bigger because it's 21.65. So there it is, negative 6.7 meter newtons. So there you go for that one there. Okay, let's go to the last problem. This is really tough. You're asked to find all the forces on the beam. Well, we're told it's a 2.2 meter beam, so you'd be very smart to do this. Put all the information into a picture as a matter of course. This is what we always do. Meters. And the mass of the beam with the mass of, so this beam is 25 kilograms, so it has a weight of 250 newtons. And the sine over here is 28 kilograms, so this is 280 newtons. That's down like this. There's another force, and there's a tension force that we do not know, so let's write tension equals question mark. Now there must also be a force on this wall that counteracts the forces to the right, but also there are forces down, so the wall must have a force on it that force must have a force on the beam that acts up to counteract the downs, and it acts to the right to counteract the lefts, because this is in a state of equilibrium. So it's got some angle here, I don't know, but this is we'll call this force of the wall. So how do we find all the forces on this beam? Well, right away I've got unknowns. I've got the tension and I've got the force of the wall. So you know what I'm going to do? I've got to get rid of one of these unknowns by putting the pivot point right at the left side of the beam. And the F wall is not a torque. I could do this as a torque problem. Eliminate that force of the wall because it doesn't provide a torque because it acts right on the pivot point. So let's do this as a torque problem. All the torques on the beam. So this is torque going this way. So this is a clockwise torque. The help wanted sign, the mass of the beam is also clockwise. And this torque of the tension is a counterclockwise torque. Therefore, it's a positive torque. So we know that the sum of all the torques has to equal 0. Let's write that down to get some points. Sum of the forces equals 0. So the counterclockwise torques must equal the clockwise torques, or else it wouldn't be in equilibrium. I think I need to clean this up so I can start to give myself some room to write. Let's get rid of this. So the sum of the torques must be equal to 0 using the pivot point on the left. Clockwise torques equal the counterclockwise torques. So the clockwise torques are 280. The sine, right down here, the sine, help wanted sine times the moment arm of 2.2 is right at the end of the beam. And the other clockwise torque is the beam itself, 250 newtons, and its weight is always placed in the middle of the beam. That's 1.10 meters. What does that equal? The clockwise torques equal the counterclockwise. That's T, the tension of the cable, times sine of 30 degrees. That's the force. The moment arm, because it acts at the end, is 2.20 meters. Okay, now I can solve for T. Let's find out what the left side equals. So the left side equals 891. And the right side is, well, sine theta is a half. A half times 2.0 is T times 1.1 meters. And so I divide both sides by 1.1. 891 divided by 1.1 equals 810. So the tension is 810 newtons. So I found one force that's on the body. But the tension now is 810. Now I have to find the force on the wall. So what I'll do is I'll find, well, it tells me here, find the force on the y component of the force on the wall and the x. Once I do my torque problems, I go to the old-fashioned sum of the forces in the y direction equals 0. That's how I'll get the force, the y component of the wall's force. So let's go to the first quarter. Sum of the forces in the y direction equals 0. What are the down forces? The ups equal the downs. So the down is the 250 newtons, and which is the rod, and the 280 is this sine, and the ups are, well, there is up. Here's the up. There's T sine theta. That's the up as well. Plus F wall y. Let me clean that up. So this is 250 plus this would be 530. Yeah, I think that's right. 530. T sine theta is now the T. Let's go back up and see. We had 810. 810 times the sine of 30. 810 times a half. So that's what the sine of 30 is. Plus F wall. Let me flatten this out. I'm getting a little sloppy here because I'm not flat. F wall y. So half of, so 530, half of, this is 405. 405 newtons plus F wall y. So all I did is the ups equal the downs. So now let me do the subtraction, see if I got the right answer. 530 minus 405 is 125. Let's see if that's right, because I have the answers up here. F wall y equals 125 newtons. Let's see if that's right. 125. Well, I got 123. I think I used 9.8 when I did the solution. It gives me 123. So now F wall x. So the sum of the forces in. Why am I so sloppy? Sum of the forces in the x direction sum of the forces, and why is that doing that? Sum of the force of the x direction equals 0. I think I'm going too fast. So the left forces equal the right forces. If I look up at my picture, there's only one left force. That's t cosine theta, the horizontal. So t cosine 30 degrees equals the F wall x. I think I'm just going too fast. Yeah, look, that's funny. There we go. So what is our t? Let's look up. 810. We found that 810 newtons is our tension. Cosine 30 degrees equals F wall x. Let's see what happens there. So I hit 30 cosine times 810 equals, let's see if that's right. Let's see, I got, okay, 687. I got 701, but I believe I worked this out with, actually with 9.8. So this is when you don't work it out with 9.8. 701 newtons. How many significant digits are we using here? Let's take a look at our numbers. We're going with three significant digits, 701. I think I have a different answer than over there because I worked out my solutions with 9.8 at one point when I developed this. Let's double check. Yep, I did. Okay, great. So that 701 is when you work it out with G is 10. That is that's the answer. That's this whole sheet. Done.